Okay, so good evening, everyone. Thank you for joining for today's session. This is the last problem solving session for the course Natural Hazards. So, today we'll be discussing the remaining topic, which is tsunami, and then after that, we'll just do a small recap through problems of the entire course up until the week before. Okay, so I'll be sharing the screen. Just let me know if it is visible to you or if you have any trouble viewing it. Now, I hope you can see the screen. And okay, thank you. Okay, so today, as I said, technically your course is for 8 weeks. So today we'll be kind of wrapping up the entire thing before your exams. So today we'll discuss tsunami at first. Okay. So I had just started it last session, but I'll again start it afresh. What do you know about the tsunami? Like, what is your idea regarding tsunami? Like, anybody can tell me? Of course, it's a natural hazard. So, what do you understand by that? Okay, so I'm assuming that you know it anyway. So, tsunami is a very huge wave that we can say, which is mostly generated by earthquakes. So, tsunami as such, it will not happen, but more or less it is triggered by some other phenomena such as earthquakes and other factors are also there, but mostly it is generated by earthquake. And as I said, the basic requirement for a tsunami to happen is when a large amount of water is displaced. So based on that, like if whatever factor is causing that, like it can be earthquake, it can be landslide, it can be volcanic eruption, it can be asteroid impacts, let it be anything, any of these. So because of this, a large volume of water is displaced, and that displaced water comes as a tsunami wave. So multiple tsunami waves will hit the coast. So tsunami is a Japanese word which essentially means harbor wave. So in Japan, as we had discussed in previous sessions also, so Japan is positioned in such a way that a lot of calamities like the tsunami, the volcanic eruptions, earthquake, all these things happen in that area. So but then we should also admire the fact that they are very well equipped to face these calamities, because of which they're still thriving. So that is something which needs to be appreciated. So as I said, tsunami can be generated by multiple factors. So the first one is the earthquake. So as I said, a lot of water needs to be displaced. So that happens with the sudden rise or fall of the seafloor. So I can just show you a figure over here. Yeah. So here you can see um, Okay, so if you look at this, so I think by this time you might already be familiar with this term subduction. So you can see here, this is the subducting plate, which is mostly the oceanic plate, and this overriding plate is largely the continental one. So what happens is when this plate is subducting, it's not a smooth subduction. Like, it's not going to just go down very easily. There might be certain portions in that subducting plate which will get stuck. So what happens is that stuck portion will still stay there, and the remaining portion is pulling it down. So slowly what will happen is a distortion will happen on the overriding plate, and as a result, if you can just compare these two, so you can see the depth over here and the depth over here is different, right? This is more deep. So as a result of this slow distortion, uh, a huge amount of water is kind of getting accumulated over here, and the moment this the stuck area ruptures, that sudden movement happens, then what will happen is whatever water is accumulated over here will get displaced in both directions, so in this direction and in this direction, as tsunami. So that is how tsunami waves spread. So, for example, the December 2004 tsunami, its origin was the Sunda Trench, like near the Sunda Trench in the Andaman subduction area. But then it spread in both directions, so that it even reached the Indian coast. So that is how tsunami waves spread. So you can just stop me wherever you find it difficult to understand. That is totally fine with me. So the next is the height of the tsunami wave. So tsunami wave is generated. So what determines the height of that wave? You might have read in news and all that, like, this much meter tall tsunami wave hit the coast, or this tsunami is this much, its dimensions, they say. So how does it, like, what determines that? So, the height of the tsunami wave, in particular the one which is caused by the earthquake, depends on the magnitude of the earthquake. So, if the magnitude is really high, then the wave will be proportional to that. Then the rupture zone area, then rate and volume displaced, and finally the depth of water above the rupture, which I just showed you. So these are the factors on which the height of the tsunami wave depends. So, like, if I'm not sure how your examination is going to be, but if they ask you, or if it is a multiple choice question, or if you have to write and they're asking, like, what are the factors determining the height of a tsunami wave, so you can just give these 4 points, which is caused by an earthquake. The size of a tsunami in the open ocean is related to the maximum displacement on a fault, which is basically what I had just shown you. How much of movement is going to happen along that fault will determine the size of that particular tsunami wave. You don't need that much of technical details, that's why I'm just skipping certain points. So tsunami generated by earthquake we have discussed. Now we are coming to tsunami which is generated by the volcanic eruptions. So same thing, like, we need to displace a huge amount of water. So how can that be done? So water can be driven upward or outward by either fast moving flows of hot volcanic ash. So if you remember from the volcanic session, I had mentioned about this volcanic ash which is accompanying the hot lava which is coming out. So if this hot volcanic ash, a huge amount of that is going to come and like, if it is a very on a coastal site, and if it is going to come into the water, so that can displace a huge amount of water and thereby trigger a tsunami. Another thing is submarine volcanic explosions. So not only the volcanic explosions which happen on the uh, land, but there are volcanic explosions which happen underneath the ocean. So that such submarine volcanic explosions can also trigger a tsunami. Another one is the collapse of volcanoes in a landslide. This I don't remember exactly where it happened, but a recent tsunami was also triggered by such a scenario, in which what happened is, this is the ocean, and on the land they had a volcano. So what happened is the one side of the volcano flank, it collapsed into the ocean. So you can imagine how much of material is coming and just plunging into the ocean. So as a result, a lot of water got displaced, which eventually triggered a tsunami. So these are few of the factors which like contributes to a tsunami as a result of the volcanic eruptions. However, compared to the tsunamis generated by earthquake, this tsunami is not very well understood. Like earthquake, we can kind of talk about how the magnitude is affecting the tsunami and all, but in this particular case, we cannot. Not much information is still available, so like studies are still going on. Then another type of tsunami is the tsunami which is generated by landslides or rock falls. So every time when I'm saying like tsunami generated by so and so factors, the basic thing you have to keep in mind is tsunami is generated when a lot of water is displaced. Now these factors trigger that displacement of water. So this thing you have to bear in mind, and then you can just talk about all these things: earthquake, volcanic eruption, or landslide. So in this case, the height of the tsunami depends on the volume of mass displacing the water and also the height of fall. So, for instance, as I said, you have water over here. This is your land, and let's say you have a mountain, something like that. So, a landslide is triggered, and landslide, whatever material is coming, it plunges into the ocean. Now, the amount or the volume of this mass which is coming, that can determine how huge the tsunami is going to be. If this mass is really high, then the tsunami wave will also be very tall. Similarly, the height of fall. So sometimes the mass may not be that much, but if it plunges from a very big height, like for instance, this is the water and then this is a cliff top, then if water is like the mass is plunging from this much of height, then what will happen? The height of fall is so high that it can displace a lot of water. So an analogy what you can think of is, let's say you take a tub, you have a bucket of water, and then you have a very big rock in your hand, and you just throw it at a smaller height. Okay, so very close to that bucket you're just throwing it in, so you can see water is displaced, right? But the same rock, if you throw from a much higher level, then the amount of water displaced will be even more. So that is what is like what I'm trying to convey over here. The height of tsunami is depending on the volume of mass displaced and also the height of fall. Fall is like from which height it is going to come down. And just like the submarine earthquake, volcanic eruption, similarly, beneath the ocean, this landslides can also happen. This is the example which I had discussed earlier also, the volcanic flank collapse. So that mostly happens in the Hawaiian Islands. So if you remember, the Hawaiian Islands are hotspot volcanoes, like volcanic chain. So in such locations, the primary factor would be the collapse of these volcanic flank. So that mostly happens in case of volcanoes which are old and which gets eroded very fast. So in such scenario, the volcanic flank collapse can happen, which in turn can trigger a tsunami. So here it can result in the displacement of thousands of cubic kilometers of water and generation of tsunamis that can be hundreds of meters high. So that's like very very tall tsunami with wave which is coming. You have to kind of imagine how tall that is going to be. Hundreds of meters is not a very small number, right? So yeah. Another one which is very rare but which is possible is the tsunami which is generated by asteroid impact. So I hope you are familiar with what an asteroid is. So that is an extraterrestrial material which is orbiting in the space. So if that comes and has an impact on the earth, or especially in the ocean, because largely our uh, earth is covered by ocean as compared to the land area, right? So if an asteroid has an impact on the ocean floor, then that is going to trigger a mega tsunami. Mega tsunami is like the largest of all tsunamis, you can say. So this is very rare. It can happen once in a million years. Million years is like 10 to the power 6 years. So that's like very a longer duration. So that's why we say it is rare. But that doesn't mean that this will not happen. It can happen, and if it does happen, it will create a very massive tsunami. Uh, Asteroid impact, not as such, I don't think we have an example, but there was a time in the past, the like if you're familiar, I don't exactly remember the name of that event, but the one in which the dinosaurs got extinct. So during that time, they're saying that there was a meteoritic impact. So that might have triggered, but I don't know for sure that if it has happened. But yeah, like this is something which is a possibility. So now that is just a brief introduction regarding tsunami and how tsunami is generated. Now you have to understand how a tsunami wave moves. As I said, once it is generated, if this is the wave, it will go in both direction, towards the shore and away from the shore. So you need to know how that happens just to have a gist of this particular hazard. So for this, you need to understand the wave characteristics. Like you have a wave, right? So wave is basically what? Something which has a crest and something which has a trough. So in this wave characteristic, we have to understand the wavelength, like the kind of the time, the length between two crusts, the height, which is basically this one, and then the period, time period, how many waves are passing per unit time, that kind of thing. So this is basically they're showing what I have drawn here. So uh, wavelength is the distance from peak to peak or the crest to crest. Period is the time for passage of one wave. One wave, how much time it is taking to move, and the height is this one or this one. So these are the characteristics which kind of tells you like how the tsunami is going to move. So in the open ocean, the height of tsunami wave is going to be small. But and that average wavelength is like 360 kilometers. So it is very broad kind of thing. Okay. So wavelength is really high, height is less. And period cannot be about, like it can be about 30 minutes. So if a ship is there in the open ocean and a tsunami wave is there, the ship will not actually feel that wave. Like it will be like a gentle wave. Although, like, if you come to the coast, so a wave with a 3-meter height in the open ocean could become 18 meters in the shallow water. So, what basically I'm trying to say is, let's say this is the open ocean, okay, and here you have the land. So this much portion is the open ocean, and over here we are coming to the shallow water. So if this particular wave is 3 meter in height in the open ocean, which maybe a ship will not feel as much, the same wave as it comes towards the coast or towards the shallow water, that is going to increase in height close to like 18 meter. 18 meter is not such a small uh, number, right? Because for an average height of a person is like 150 centimeter, like 1.5 meters. So you can imagine how high this 18 meter is going to be. So this is a diagrammatic representation of that. So the reason for that is that in the open ocean, the depth from the surface to the floor is higher. but as you come closer, it's kind of getting squeezed. So it's getting squeezed and its height is increasing. This brings us to wind waves. So wind waves, like caused by wind, basically, as the name suggests, they have short wavelength. They touch bottom near the shore and they will break near the shore. So if you have been to the beach, you know, right? When the wave comes and when it comes at a particular height, and then as it strikes the uh, like the coast, it will just dissipate. Like it will not have that much energy and it will just drop. However, when it comes to tsunami waves, they have long wavelength. They touch bottom everywhere in the ocean because they're so huge. They can touch the bottom everywhere, and as a result, they will not get dissipated even when they hit the coast. That's why, like when a tsunami wave hits, that water spreads to a longer distance because the energy is so high. Now, the tsunami waves are faster in the open ocean, although their height is less, they are faster. So, it's like 870 kilometer per hour. So, once a tsunami is triggered, it can move in such a speed that it can hit the coast like in both directions. So, here, if you see, this is water depth. So, waves are faster in deeper water. So, if you look at the deeper water area, this is the point, right? So let's say we are taking this 4000 depth. The wave velocity is 700 kilometer per hour. That's a huge number. But as you come closer to the shore, let's say something around, this might be 100, uh, yeah, so 200 meter, then the velocity is like 159. So the velocity is less, but that height is going to be really big. So the velocity of tsunami waves can be calculated by this formula, which is c is the velocity in meter per second. C is equal to root of g, which is the acceleration due to gravity or the gravitational acceleration, and d is the depth in meters. So just keep this equation in mind because I have a problem regarding this towards the end of this session. So you can just solve it. So the formula for a velocity of tsunami wave is c is equal to root of g into d. So an example that they're giving here is if d is like 4600 meters, or yeah, in the d portion, then the velocity in d portion will be 3 into 1 3.13 into 67.8, which is basically the root of this one. So it is 763 kilometer per hour, which is the speed of some jet aircraft. So for people who have noticed this jet aircraft moving, you won't be able to see it for a longer time compared to the airplane, right? So that kind of difference is there. It moves really fast in the open ocean. And if the d is 100 meters, if you just multiply this, and then you're going to get it as 112, which is the speed of a freeway traffic, normal traffic speed. That's how a tsunami wave will be closer to the shore. So just keep this equation in mind. C is equal to root of GD, or C is equal to 3.13 root of D. 3.13 is because we are just kind of taking the root of 9.8 and then just taking it like this. So 3.13 into D. So here, if you take a look at this, this is at Kalutara in Sri Lanka on the December 2004 wave, like tsunami. So the first wave of tsunami surrounds all the houses in the satellite view. Okay, so here the wave is surrounding all the houses, and then it just recedes back. So that's what it is showing. It touches and then it goes back. Now, if you take a look at the larger area, so you can see there is a huge area which is kind of displaced. So if you have read about tsunami, you must have read that before a tsunami, a lot of water gets displaced so that the sea recedes into the ocean. You can see a lot of land area or the shore area before a tsunami strikes. So this red dotted line that they are showing is the normal beach. Usually water would have come till here, but just before a tsunami wave, it has receded to almost this much distance. So this was a problem because not many people were aware about this. And what happened is that when the water recedes to this much of distance, then a lot of fish gets exposed, right? So people got very curious, and they were that curiosity kind of resulted in a lot of uh, casualties, you can say. Like, people were curious, they went closer to the sea, and before they knew it, the tsunami wave struck. So this is something which should have been, brought into this community, like their knowledge that this tsunami is a natural hazard, and before a tsunami strikes, so and so things happen. So that kind of warning was not there, or people were not aware, and because of which a lot of casualties happened during this particular tsunami. So this is yet another figure. This is the people on the Krabi beach in Thailand. So you can just see, right? They are looking at this big wave which is approaching the shore, and they didn't know what exactly was coming. And then you can see just few seconds later, the wave is just coming really fast, and then they don't have enough time to escape. So the first tsunami wave need not be the highest. Just because the first big wave struck, you should not think that that is it. That is not the case. Wave periods can vary between 10 to 35 minutes. So maybe after 35 minutes, even bigger wave can strike the shore. So here I have a small video regarding tsunami. So we can just watch it. So that kind of summarizes what I had told till now. So regarding the height of the tsunami wave, the factors which trigger tsunami wave. So this kind of gives you a pictorial understanding of what I was talking about. So if you have any doubts up until now, you can just ask me, or I'll continue. Aftershock might not. The thing is, the magnitude of the earthquake kind of determines the tsunami. Because if the magnitude is really high, then you know that the energy that it is going to give out is going to be really high. So, in proportion to that, the wave is going to form. So, if the aftershock is big enough, then yeah, it can trigger a tsunami. But mostly aftershocks are not as big as the main shock, so main event. So Uh, not exactly aftershocks. I don't think I have any examples to state, because most of the time, because especially in this December 2004 tsunami case, that was the main event. Main event triggered the tsunami, and then a few months later, I think till March of the next year, like 2005, a few areas surrounding these regions, like the Sundat area, they experienced the aftershock, but that did not trigger a tsunami. So uh, that's something I can think of. But yeah, like the basic thing you have to keep in mind is that the magnitude of the earthquake determines whether a tsunami is going to be triggered, or even if the tsunami is triggered, how tall or of how strong that is going to be is dependent on the magnitude. Okay. So now we know what tsunami is, how it is formed, and all those features regarding tsunami. So then we need to think about the tsunami hazard mitigation. So as basically this comes under the disaster management part, right? So we know tsunami is a hazard because it is causing a lot of trouble for the people and their property. So we need to be prepared for it. So what all things can be done? So, land use planning is the first thing. So, land use planning is basically we need to restrict building to heights above those that would potentially be flooded. So, like sometimes if let's say this is the coastline, and then you have the land area over here. So you know that a particular uh, till a particular region, it's definitely going to be affected by the tsunami wave. So it was always better you plan properly and then construct buildings in such a way that they are at a little bit more higher level, and so that even if it is flooded, you have a option to go even higher in that building. And if in certain scenarios where you don't have the higher areas where you can build these structures, in such cases, that potential tsunami impact should be considered while planning. Like the way you are going to plan the construction, all those things needs to be done. Because the thing is that you cannot, tsunamis bound to happen in the regions where you have the subductions, like where which is prone to earthquake or volcanic eruption or landslide. So then the only thing that you can do is be prepared for it, like minimize the amount of damage that it will cause when it strikes. Then streets and buildings perpendicular to waves survive better, as waves will be able to move further and dissipate. So I think I might have a diagram for that, or else I'll just explain it to you. So, let's say the wave is coming like this. So, if the buildings are constructed, so this is the wave direction. So, if buildings are constructed perpendicular to it rather than along it, so like one condition is okay. This first condition is this is the wave coming and buildings are constructed like this. The second situation is the wave is coming like this and buildings are constructed in this manner. So what happens is, if the wave comes like this and buildings are perpendicular to it, then when the wave hits, it has a chance of going further, like longer distances, and it will dissipate very quickly. But if this is the case, this entire area is going to get the full energy of that wave, because it is along the direction of the wave. So such planning needs to be done along the coast. Then well-rooted vegetation can also slow down waves. So in certain beaches, you might have seen certain tall trees present. So if they have well-rooted vegetation in such shores, then they can also dissipate this energy. The basic thing is that tsunami wave has a lot of energy accumulated. So that energy needs to be dissipated as quickly as possible, so that it doesn't affect too many people. So in order to facilitate that, either you should plan the construction of buildings in such a way, or you should make sure that you have well rooted vegetation present in order to slow down these waves. Another thing is the tsunami protection walls, like the sea walls, most places people construct. So that is another thing, so that you have sufficient time to do the evacuation and all those things. Because most of the time, since this time period between the waves can also be like this 10 to 30 minutes, so people don't get sufficient time to kind of take people away from these highly impacted zone. So in order to buy that much time, like if you get some time, and that will help you to take your uh, necessary things and save yourself, then for that you have to make sure of some either one or all of these is implemented. So this is a tsunami protection wall, which is found in Japan. So as I said, Japanese, they are very much prone to all kind of hazards. So they are well prepared. But still, there was an event in which the tsunami even came above this wall. So I don't remember exactly the name of that, but there was a tsunami event. I think uh, there was it was triggered by an earthquake only. So something that nuclear plant was also disrupted, and then that was a very high energy tsunami event. So that kind of came over the wall, but because the wall was present, that energy got dissipated. So such things work in favor if you have uh, such structures built. So, depending on their distance from the epicenter of an earthquake, tsunami waves can appear within a few minutes to several hours after the earthquake. So, if you have a major earthquake event, say like at in the morning, like 10 a.m. in the morning, a particular area experienced a major earthquake. So, just because the tsunami wave doesn't appear in like a few minutes doesn't mean that tsunami will not happen. Like tsunami, like that hazard will not occur. It can happen even after several hours. So, monitoring the sea floor, monitoring such earthquake events, all these things are very much necessary in order to be better prepared for such events. So, warning systems can predict tsunami travel time. This is basically understanding what kind of earthquake was generated, where it was generated, how strong that earthquake is, like the magnitude of the earthquake, and also where its epicenter is. So, depending on that, warning needs to be given out. So in Pacific Ocean, they are kind of well prepared for this. So 26 countries keep receiving the warning, as in when a tsunami is about to strike. So here you can see this is the like these colors kind of show the estimated travel time of the tsunami in the Pacific and the Atlantic Ocean. This, if you remember, in the earthquake part, uh, we had talked about this Chile 1960 earthquake, right? So that was the higher uh, magnitude earthquake, like about 9 magnitude earthquake. So that triggered a tsunami. So its epicenter, close to the epicenter, the waves were very quickly it reached the shore, and then as it moved further, it kind of took a longer time. So here they have written also. So from the Alaska earthquake, for example, the first tsunami wave reached Hawaii in approximately 6.5 hours after the earthquake, and it reached Japan after 7 hours. So that kind of time difference will be there. So if you have proper warning systems, then these all the authorities, they can just evacuate and take necessary measures. So this is a deep ocean assessment and reporting of tsunami. That is a buoy system. So what they do is they kind of take this instrument, they put it in the open ocean, and then there is a pressure sensor on the ocean floor. They put that also. So this here diagrammatically you can see. So pressure sensor is here, and the receiver, that transducer, it is here. So what happens is, if any kind of variation is there, like uh, in a wave height, some kind of a variation is there in the wave height, or some pressure is added, then this sensor will transmit it to this device, and from that it will be transmitted to the satellite. So that way they kind of monitor the ocean floor and a potential tsunami event. So once the danger signals of a tsunami are noticed, the first and prior thing that needs to be done is for the people to move to the higher grounds. Just a moment, let me just plug in my laptop. Okay. So immediately, the first and foremost thing that needs to be done is for people to move to the higher grounds. So as I had mentioned earlier also, where people were not aware of these particular details, uh, they got curious and they went in when the sea receded. So that was a very only that people did it only because they were not aware. If they knew it, they would have taken that time to run to the higher grounds. So now most that awareness has increased, but then back in that time it was not. So at least tens of meters above sea level height you should try to go. That kind of ensures that at least you will not be harmed as much, or move further inland, because there will be a limit till which the seawater is going to come. So beyond that, if you can go, that is much much better. So studying these tsunami deposits and modeling helps in preparing hazard assessment maps. This is another way how you can be prepared for a future tsunami event. So what they do is that when a tsunami strikes, then because it is a high energy wave and it brings all kind of material, so it has a particular kind of characteristic deposits within the ground, and studying those deposits will and thereby modeling will help in preparing the hazard assessment map. So you can kind of understand till which distance that tsunami wave struck, and then in future what is the possibility. So all those things you can kind of study. So if you can model the tsunami, then there you can actually enhance the mitigation measures. So the primary objective of this modeling is to simulate tsunami waves for generating the amplitude and travel time maps. So it's kind of like a simulation thing. So we are just simulating the tsunami waves, and then we'll generate the height. That is to just understand the height of the wave and how much time it is taking to move. And using this results, we can study the future impact in such locations. So this is just a case study kind of thing. So the 2004 December tsunami that was caused when the Indian plate. So we know where the Indian plate is, right? So that is moving northeast. So for example, this is India. So the Indian plate as such, it is moving in the northeast direction. Okay. So that is moving at 6 centimeter per year relative to the Burma plate over here. So this is the Indian plate and then you have the Burma plate. So 10 years prior to this event, that 10 years is like what, 1994, right? So that time there were 40 earthquake events larger than 5.5 magnitude, but none of them generated a tsunami. Like there were multiple earthquake events which had a magnitude greater than 5.5, but none of them generated a tsunami. Now when people studied this old events that had happened in this December, like this region, so what they understood is that giant events occurred once in every 230 years in this particular area. So the kind of time period that they could understand is 230 years. That's why like 40 earthquakes happening like in 1994, uh, it didn't trigger a tsunami, but then probably 2004 was kind of coming in that 230-year time period. So that kind of resulted in a tsunami. So the subduction boundary between the two plates had been locked for hundreds of years, resulting in a bulge in the overriding Burma plate. So if you remember the diagram I showed you in the initial part, so if this is the subducting plate and this is the overriding plate, what happens is if this particular, some area in that subducting plate is stuck and still this is trying to pull it down, then what will happen is eventually a bulge will come in the overriding plate. That is what they're talking here. So a bulge appeared in this Burma plate. So this water displacement depth kind of increased. So when the December 2004 tsunami, like earthquake struck, that was like 9 magnitude, which is really, really high. So when that earthquake struck, then that kind of triggered a tsunami. So the problem with this was that the earthquake itself caused a lot of damage in Sumatra, and then followed by the tsunami that kind of wiped a lot of area in Indonesia. So here you can see the sudden ocean floor rise resulted in a huge wave which moved at speeds more than 700 kilometer per hour, which is like very quick, right? So and it reached the shore within like 15 minutes. So that's not a very like we don't have enough time to uh, rush to higher grounds. So if there was a proper warning system in place, then this might not have happened. So here, this is thing which happened. So a 5 meter high tsunami wave, it struck the northernmost Sumatra, and it wiped almost like 25 kilometer of the capital of Sumatra, and like 8 kilometer inland and 24 meter high kind of that much height it affected. It also affected western Thailand, east coast of Sri Lanka in within like 2 hours, and the east coast of India shortly thereafter. Like people from Tamil Nadu might be knowing, like the effect of tsunami was felt there also. So this caused a huge casualty because people didn't know that there was a possibility of tsunami because people were still on the coast when the tsunami struck. Had there been a proper warning system, then they would have evacuated people to higher grounds. So that time we didn't have an proper warning system, but after this event, uh, like the authorities took an effort to install a proper warning system in place. Another thing is the lack of public education. So warning system was not there, and at the same time people were very much new to this term known as tsunami, like only because like they were not aware of it, they were not taught about it. So another example that can be pointed out is that a 10-year-old girl who had learned about tsunami in school yelled to people around her to run uphill when she saw the sea recede before the first wave. So even a 10-year-old girl understood that because she learned it in school. But the adults who were unaware of this didn't take the necessary measures required at the particular time. So whoever listened to this little girl, they could go to higher grounds. But whoever didn't listen and went closer to the receding sea, they got wiped off. So, although the casualties were really high during the December 2004 tsunami, uh, because of the efforts of this little girl and another similar situation in uh, by a dock worker, uh, they kind of both of them together saved 1,500 lives. Had it not been for them, then these 1,500 people would also have perished in the tsunami. So, this kind of tells us the necessity of a proper warning system and proper education regarding tsunami. So, the next time that you witness an earthquake of a very high magnitude and you are near the coast, then you will know that I have to expect or consider the possibility of a tsunami. Or if you see the seawater receding, that itself gives you a idea that okay, water is going so much in, which means a tsunami is going to strike the coast, so I have to go to higher grounds or further away from the coast. So that kind of information needs to be spread. So that is regarding tsunami. And this is a topic which one of you asked. I don't know if he is present, like Zariful Aslam, I think. So he had asked me regarding glacial lakes and glacial lake outburst. So I have just one or two slides on that. So we'll just briefly discuss that and go to the problems. So glacial lakes are water body which originates from glacier, as the name suggests. So how do they form? So if you look at the mountains, especially in the Indian context, we can talk about the Himalayas, right? So Himalayas, they have a lot of glaciers present, moving ice for that matter. So when this glacier moves, what will happen is, let's say, uh, this is a glacier which is going in this direction, okay, and you have the ground over here. So what will happen is when the glacier moves over the ground, it is going to take material from the ground, like stones or pebbles or whatever, some sharp material will get attached to the bottom of the glacier, and as it moves further, these rocks will kind of there will be a friction, and that will create small grooves or depressions in the ground. Then what happens is, if this kind of happens for a longer period of time, that small depression will become big, and then finally it will become bigger enough to be called as a lake. So it becomes a lake when the glacier retreats and the melt water, like the ice which melts, and that subsequently whatever water is formed, when that fills this hole which is left behind, we call it as a glacial lake. Now that is one way how glacial lake can be formed. Another way is if you have a ice dam. So dams, you know, right? Dams will restrict the water flow. So similarly, uh, ice dam will form when a surging glacier. Surging glacier is a glacier which moves like 100 times faster than a natural like a normal glacier. So when that moves, and it will dam up meltwater, like you have a meltwater flowing or something like this, and when the glacier or the ice comes and blocks it, it will create a kind of a glacial lake. These are mainly two ways how glacial lakes are formed. Now, this brings us to the glacial lake outburst flood. Actually, this is the topic that he had asked me to discuss. I just talked about glacial lake because for those who are not familiar, I thought I should introduce that. So, yes, huh? No, no. Tsunami. See, normal waves of water. That waves have a. They are called as wind waves. Okay, so they have a particular height above which they are not going to form, because the thing is, I had mentioned that example also, but I can show it over here. Okay, so what happens is, let's say this is the okay, this is the shoreline. So this is the coast and this is the sea. So the normal waves when they come, so they'll be big in the ocean, and as they come closer to the sea, I mean coast, they will become smaller. They will hit and they'll just dissipate. They are not going to have that much of an impact. Okay. So the thing is, this wave, that is the normal wave or the wind wave, that only affects the top surface of the ocean. It will not go to the higher depth. So because of which, as it comes closer to the coast, it will its energy kind of goes off, and then it will just hit, and as you see in the beaches, that is the normal thing. But in case of tsunami, what happens is, when a tsunami wave is formed, its effect is completely through the depth of the ocean. So if you remember in the video also I had shown, so what happens is, this is a wind wave. You have a tsunami wave which has a lesser height in the open ocean. So that I was talking about, like let's say a tsunami wave is like 3 meter in the open ocean. So just because you see 3 meter above the ocean surface doesn't mean that that is the height of the tsunami. The entire tsunami wave is affecting the entire depth of the ocean. Then as you, no, no. So no, what I'm saying is, whatever, like yeah, subsequent waves will become larger. That is true. What I'm saying is that in comparison to the wind wave, any tsunami wave will have a higher energy compared to the wind wave. Okay. So what happens is, if it is in the open ocean, so this is a wind wave which will only affect, say, this much of depth of the ocean. So it is not affecting this much depth, right? So it will dissipate very easily as it comes to the coast. But when you have a tsunami wave, this you can consider as a tsunami wave. So that wave has a complete effect of in the entire depth of that ocean. So what will happen is, initially that wave is like this, okay? Now when it comes closer to the coast, its energy is still not dissipated, because the thing is, tsunami wave, as I said, depending on the energy of that earthquake, if the earthquake is very high magnitude earthquake, then the tsunami wave can hit very quickly, because it has a lot of energy, like within 15 minutes that is going to happen. So that 15 minutes is not sufficient for this wave energy to dissipate. So what will happen is, as it comes closer to the coast, so this, let's say this is the coast, so depth is decreasing, right? But what will happen is, here that wave height is less, it is broader, but as it comes to the coast, it is kind of like, if you push a paper from both sides, you see how its height is increasing, right? So that kind of an effect like that. So what will happen is, closer to the coast, that energy is still sufficient, so it becomes a taller one. So throughout its point of origin till it hits the coast, the entire depth that tsunami wave is going to affect. Okay. Okay, so if you any of you have any doubt regarding the tsunami part, you can just stop me and ask. This is I'm going to discuss about the glacial lake outburst flood. That's just a brief thing. Anyone has any question regarding the tsunami? Okay, so pattern. Okay, that even I am also not very sure. Like they've not conveyed anything as such, but I think both kind of problems might be there. Like MCQ type will also be there, and maybe short answer type because it's your online exam, right? So I think it's better. Like I don't think you might have such longer ones, but it's better to be prepared for short answer types also. If I get to know anything, I'll share it with you like on the forum. But I don't know. Like as of now, I also don't know regarding that. What? I'm sorry. Like that I don't know for sure. Uh, I'll have to ask the course instructor, and then maybe I can convey it to you. Or maybe you can put the query in the forum, so then they can directly answer regarding the exam. Okay. So, okay, I'm moving forward with this topic. So, glacial lake outburst flood. So, as the name suggests, whatever lake has formed, it is, uh, water is going breaching and coming out. So, that is glacial lake outburst. The plain idea. So, the glacial lakes, which I said how they are formed, so they can burst in the absence of a safe drainage system. So, the thing is that uh, glacial lakes, if they do not have a proper outlet or something like that, what will happen is when the melt water increases, or like if there is a lot of water coming into this lake which the lake boundary cannot hold, then what will happen is it will break or burst, and then that entire amount of water is going to flow off. So this is what happened in the Kedarnath flood 2013, because there was this Chorabari glacial lake that because of the cloud burst, a lot of water came into the Chorabari glacial lake, and then that burst, and then the entire water and accompanying material hit the Kedarnath area. So that's why I specifically took this up. So uh, yeah, so basically if idea is that if a lot of water which the glacial lake boundaries cannot handle comes into the glacial lake, then there is a very big chance for the glacial lake to fail and burst. So a study which was conducted in 2021, the like 3 years back, that validates that the region most susceptible to glacial outburst in the Indian scenario, especially in the Himalayas, is the eastern Himalayas. Because why? The reason is that eastern Himalayas, when compared to the western Himalayas, they are a bit slightly more on the warmer side. Okay, so the chance of increased meltwater input is more in the eastern Himalayas. So, therefore, people in that area need to be aware and prepared for a glacial lake outburst flood. So, some mitigation measures for this glacial lake outburst is reducing the volume of water. So, the reason for the outburst is because water volume is increasing. So, externally, if you can reduce that volume of water, that can kind of reduce the chance of an outburst. So this can be done by controlled breaching, that is basically kind of excavating a channel or blasting or something, and then kind of creating a path for that excess water to flow out. Or else you have to construct a structure around the lake, a lake boundary, or with available stones, or like very rigid material, so that that boundary is kind of uh, maintained intact, and it will not break and release that much amount of water. Or another thing is pumping or siphoning out the water from the lake. So the basic thing is to reduce the volume of water. That is one mitigation measure. Then the preventive measures around the lake area. So these mitigation measures can be done within the lake, and then around the lake area also you have to take some preventive measures. So the first one is the protecting infrastructure against the destructive forces of the surge. So what happens is that suddenly a lot of water is coming. So you have to build structures which can kind of like this tsunami wall, you can say. So you have to make structures in such a way that that much amount of water doesn't directly affect the people, rather it hits somewhere and then it dissipates, that kind of thing. Then monitoring and early warning system. So there are people like climatologists or hydrologists, whoever. What they do is they keep studying these glacial lakes, their area, the water input, all those things, using satellite data, on ground data, and they keep monitoring such areas, so that they can understand like if that volume is beyond the capacity of that lake, or if that lake is there is a chance for that lake to fail. So that was regarding the tsunami part and the glacial lake outburst. So if you don't have any questions, then I can move on to the problem part. I have a lot of problems to revise. That's why I might have rushed in a bit. But then, if you want me to repeat any topic, I'm more than happy to do that. Okay, so then I'll move on to the problems. You can stop me wherever you want me to stop. So, based on the discussion that we did today, you have to give me the answers. So, when the tsunami reaches the coast, what happens to its amplitude? And then it crashes with the area getting inundated. Inundated is basically getting submerged under the water. So, what happens to the amplitude of the tsunami when it reaches the coast? Or height of the tsunami for that matter? Yes, so some of you have given me the answer in the chat box. So the answer is it increases. So just now also I had explained it, right? In the open ocean, height is less, and as it comes closer to the coast, it is going to increase. The tsunami modeling requires the dash to simulate the wave height and travel time maps. Like a particular information is necessary in order to simulate this wave height and travel time maps. Anybody? Okay, so I'll give you the answer then. So that is fault parameters. So fault parameters we require because tsunami is mostly, like as I said, it can be caused by several reasons, but mostly it is related to earthquake. So most of the tsunami modeling is based on that. So earthquake, it is related to fault and fault movement. So therefore, fault, you need to know fault parameters in order to do the tsunami modeling. What information does the inundation map give? In the event of a tsunami, or as a warning kind of thing, an inundation map is prepared. So, what does an inundation map give? I just said what inundation means, so you can just make a guess. Anybody? Okay, someone has given it in the chat, I think. So, yeah, submergence only, but like the area submerged. So, the extent of tsunami deposit in the coastal areas. So, because wherever that tsunami water has reached, till that extent, the tsunami deposit will also reach. So, the inundation map tells you how far the tsunami deposit is present. The 2004 Indian Ocean tsunami is regarded as dash tsunami for Indian subcontinent. I don't think I have put in the options, so I'll give you the answer for this because this question is a bit confusing. So it is a far source tsunami. The reason is this tsunami originated in the near the Sumatra region, and then compared to its point of origin and the Indian subcontinent, that is kind of really far. So we call it as a far source tsunami in that particular case. So the 2004 Indian Ocean tsunami is regarded as a far source tsunami for Indian subcontinent. This is why I had asked you to remember that formula. So you need to calculate the tsunami wave velocity at a depth of A 150 meter and B 3000 meter. So this is the shallow part, and this is the open ocean. So can you just quickly on your phones, or if you have a calculator available, can you just quickly do it and tell me what is the answer? Or can anyone tell me what is the formula first to find the tsunami wave velocity? Just give it a try. If anyone has got the answer, just put it in the chat box, or you can just tell me. Or for those of you who doesn't know, the formula is C is equal to root of G into D, where D is the depth, C is the velocity, and G is acceleration due to gravity. Or a more simplified answer is 3.13 root of D. So only thing that you have to do is put this D over here. So just do it and just tell me the answer. Okay, one of you have given me the answer. And what about the next one? Okay. So the answer is 38.3 meter per second for 150 meter depth and 171.44 or as you had given. So I just put this so that you can just use that formula and find it out. So even if something related to that comes for your exam, it's a practice kind of problem. Okay. Now we'll do a recap of this entire course in the form of problems. Like I might have already discussed these problems before, but this is just to refresh your memory if you have forgotten things or not. So I can explain it as we go. So the first question is, earthquakes and volcanism are dash that threatens or acts hazardously in a defined space and time. The options are anthropogenic process, exogenic process, endogenic process, none of the above. You can either tell me the answer or you can put it in the chat. Yes. So the answer is endogenic process. So endogenic is what? Something which is happening within the earth. So earthquake and volcanism, their point of origin is within the earth. So they are endogenic processes. Exogenic means something which happens on the surface of the earth. And anthropogenic is something which is as a result of human activity. The next question is, when two tectonic plates move towards each other, then those are called dash plate margins. Constructive, transform, destructive, none of the above. When two plates move towards each other, what do you call such plate margins? You have to think like they are moving towards each other. Yes, the answer is destructive. Because what happens? There are two scenarios, right? So this is a plate, this is another plate, this plate is moving here, this plate is moving here. Now if this plate has a higher density, what will happen when they approach, this plate will go down beneath the other plate. So basically something is getting destroyed in the process. Or in if these had comparable density, then they will collide and again material is getting destroyed. So they are destructive plate margin. If on the other hand these plates were moving away from each other, then what will happen? In the gap some amount of lava or magma will come, it will solidify, so something is getting added to it. So in such scenario we call it as constructive plate margins. But in this particular question, the plates are moving towards each other, they are getting destroyed, so we call it as destructive plate margin. So I have put a diagram also over here, so that will be easier for you to understand. So this is constructive, where you have material getting added, destructive where you are losing material, and conservative where neither you are gaining any material nor you are losing any material. The next question is, the Himalayan orogeny is a classic example of collision tectonics, mid-oceanic ridge mountain system, subduction volcanism, continental rift. You have to think and give me the answer. What is the example? How did the Himalayas form? Or that is another way to frame the question. Yes. So the answer is collision tectonics. So the Himalayan mountain chain, they formed as a result of the collision of the Indian plate with the Eurasian plate. So what initially happened is that the Indian plate was somewhere in the southern. I'm not drawing it very properly, but anyway. So the Indian plate was somewhere in the southern hemisphere. Then it started moving towards the north in kind of in this direction. So in this process, uh, it approached the Eurasian plate. So initially, there was a sea present in between, which is known as the Tethys Sea. So then that subduction happened, and then these Indian plate and Eurasian plate collided. So once that collision happened, the Himalayan mountain chain formed. So if you check something related to this, you can see the video of this also. So basically, Himalayan orogeny is a classic example of collision tectonics. So this was how it formed. Like 60 million years ago, this was India, this was Asia or Eurasia. So it's kind some water was present. So this was subducting. Then a point came when the entire ocean or sea subducted beneath, and both lands collided with each other. And then it formed the Himalayas, and behind that we have the Tibetan plateau. A system which can exchange energy with its surroundings but not matter is termed as. Energy is exchanged but not matter. So these are the options. Uh, what would you say? Okay. Uh, Anybody else wants to give the answer? Okay. So the answer is closed system. You're right. So basically, we have the isolated system which doesn't exchange energy or matter. Then we have the closed system in which energy is exchanged. And then we have the open system in which both are exchanged. So I had also mentioned a classic example of this comparison of these two. So if you have a hot tea in a flask, that is a closed system. Because flask, I don't know, hot tea in a flask, every time I confuse it. So hot tea in a flask is an isolated system, and if you have a hot tea in a bottle, that is a closed system. Why? Because in a flask, that tea will remain hot, and the amount is also same. But when it comes to the bottle of tea, then what will happen? Some amount of heat is dissipated. After some time, that tea will become cold. So that is the example of closed system. And open system is when you keep it open. That's as simple as that. The earth releases its energy in the form of dash radiation. What kind of radiation? Short wave, long wave, both short wave and long wave, none of the above. Okay, so the answer is long wave. So it comes like the one which is coming from the sun, it is short wave radiation, and then when the one which is going back is the long wave radiation. Identify the correct statement about cyclones. High speed winds circulate around a high pressure region. High speed winds circulate around a low pressure region. The wind direction is clockwise in southern hemisphere. Both B and C. Okay. So the answer is both B and C. So only thing you have to remember is cyclones form in a region where you have a low pressure zone. Okay, so that is one thing which is right. So that is true. And the other thing is wind direction is clockwise in the southern hemisphere. Can just I'm just asking, building on this part. So can anyone tell me why the wind direction is clockwise in the southern hemisphere, or what is the reason for that? Yes, you're right. So the answer is Coriolis force. A location where an earthquake originates is termed as hypocenter, ground zero, epicenter, fault line. Yes, you're right. So the answer is hypocenter. Oh, okay, sorry. You have given me the answer as C. Okay, the answer is hypocenter because epicenter, I think I have a diagram here, yeah. So this is the point of origin of the earthquake, and the point directly above it on the surface is the epicenter. So when you are asked the point of origin, That is the focus or the hypocenter. Epicenter is that point which is present directly above the focus or hypocenter. The dash region records around 70% of the world's earthquakes, measuring up to magnitude 7 or more. So these are the options. Which is the region which has accounts for 70% of the world's earthquake? Yeah, you're right. So it is the Asia Pacific region. So that is the region where you have the uh, Pacific Ring of Fire. So you have a lot of subduction zones present in the form of a ring kind of thing. So those regions are very much vulnerable to earthquakes. In US, the Dash earthquake with magnitude 7.9 moved the fault by 18 feet, and the pipeline above the ground did not face any kind of damage. So these are the options: San Andreas, Denali, Palu, Hayward. This question is specifically asked because this is a classic example of a good mitigation measure taken during an earthquake event. That's why this is a kind of an important part. So, do you remember this example? Okay, so if you don't remember, I'm just refreshing your memory. The answer is Denali fault. So the thing is, in this particular case, what the people did is they were aware of where the fault is, and they kind of did several studies in which they estimated how much like the maximum magnitude of earthquake is possible along this fault. Then accordingly what they did is they made this pipeline which carried crude oil along this fault, so that when this earthquake struck along the Denali fault, the pipeline was not damaged. So that is a classic example of a good mitigation measure. So I don't know, like if in your examination, if they ask you in MCQ pattern, they might ask in this way. But otherwise, if they ask you, give an example of a proper mitigation measure done in order to account for an earthquake damage, then you can give this as an example. The next question is: in some volcanic eruptions, mud flows resulted due to snow cover are termed as debris flow, lahar flow, snow mud flow, none of the above. Any answers? What do you call the mud flow, which is, uh, or to put it in a plain format? Yeah. So Krishna Priya has given the answer. So the answer is lahar flow. So lahar flow forms when the like snow-capped mountains, volcanic mountains are there. When it erupts, this snow melts, and along with all the material along the flank, it was going to come down, along with the volcanic material also. So it's called as lahar flow. Uh, the difference in arrival time between the dash and dash reveals the distance from a dash to an earthquake. So already the options are there. So yes, the answer is B, which is the primary and secondary wave, and it kind of tells the distance from a seismograph to an earthquake. Isoseismal denotes a contour or line on a map showing an area experienced uh, which of the following? Like, what does an isoseismal map tell you? Okay, so the answer is B. That is similar earthquake intensity. So such isoseismal maps kind of helps you in understanding the areas and all. So yeah, this is the next question. Seismic microresonation is done on the basis of computed peak ground acceleration, which in turn depends on what? Okay, so you have given the answer, that is lithology of the area. So the thing is, when you do this seismic zonation on a large scale, then we consider the magnitude of the earthquake and all those things. But if you take a smaller area and then you have to see how the earthquake is affecting that particular area, uh, that is known as microzonation. In order to do that, we need to know the peak ground acceleration, which in turn depends on the lithology of the area. I'm just assuming that all of you are understanding these topics. So if you don't, just stop me and you can ask me. Dash is the surface manifestation of the fault plane that shows the lateral propagation of faulting in the earthquake. I don't think I have put any options for this. So, like, if you know, you can just put the answer in the chat box. What is that term for the surface manifestation of the fault plane, which shows the lateral propagation of faulting in the earthquake? Okay, so not footwall. Okay, I'll draw it and show to you. So the answer is fault rupture. Okay. So the footwall is not a surface manifestation, that is rather something which is beneath the surface. So if this is the footwall, then this is the hanging wall, and this is how the fault is moving. Then this thing which you see on the surface, because beneath the surface it is happening like a plane kind of thing, but on the surface it's kind of like a line. So that is known as the fault rupture. Or it is also known as surface rupture, as it is given in this diagram. The major volcanoes are along the dash, spewing lava intermittently on the Earth's surface. This is kind of like that question in which I asked where you find the 70% of earthquake prone area. So, can you make a guess? Like, where do you find the major volcanoes? Plate boundaries is right. I'm just asking specifically, like, in that previous one I asked, I gave you the options, right? This pacific, okay, the answer is Pacific. Okay, oh, I have the options also. I'm sorry. Okay, answer is Pacific Rim. So if I don't think I have put the map in this. But the basic understanding is that if you have the Pacific Ocean over here, okay, it's the largest one, right? So in a particular area, uh, you have all these subduction zones and then some mid-oceanic ridges. So all these regions are prone to earthquakes as well as volcanic eruptions, because subduction zones are also associated with volcanic arc. So it is answer is Pacific Rim. So 70% of earthquake you find it in the Asia Pacific zone, and the major volcanoes. Basically the Asia Pacific zone and the Pacific Ring is more or less similar only. Or you might have also heard about the Ring of Fire. That is what I'm referring to. The next question, the dash were formed near the end of Cretaceous period, like 65 million years ago, due to volcanic activity when the Indian continent started drifting from the main Gondwana land. Or to put it simply, when the Indian continent started moving from the southern hemisphere to the northern hemisphere, at around 65 million years, a particular feature formed. You have to remember this is before the formation of Himalayas. Okay, so between that movement and the formation of Himalayas, something else formed. What is that? So if people from Maharashtra are here, then they can easily tell me this. Anyone? Okay, oh, sorry, I already clicked it. So the answer is Deccan traps. So, as I said, when the Indian plate moved from that southern part to the northeast part, so what happened at one point of time, it crossed over there was a hot spot. Okay, hot spot is uh, kind of a mantle plume was present, and then when the Indian subcontinent moved over this particular area, so then all kind of magma lava came out and it formed the Deccan traps. These are known as flood basalt. You don't need that much technical thing, that's why I'm not mentioning it, but the answer is Deccan traps. Because there is a chance that sometimes like people who are not familiar with this, they have a tendency to give the answer as the Himalayas, but the Himalayas formed later on, like around like 40 million years or so. This formed in like 65 million years. Which volcano destroyed Pompeii and killed 16,000 people? The name of that volcano. Anyone? What is the name of that volcano which destroyed Pompeii and killed 16,000 people? Yes, you're right. So Krishna Priya has given the answer. The answer is Mount Vesuvius. The downward movement of slope material under the influence of dash is termed as mass movement or landslide. What is that factor? Yeah, so Jitu Raj has given the answer. The answer is gravity. When the slope material gets water saturated, there is an increase in dash force. What will happen when the you just have to think what will happen uh, when the slope material gets saturated with water. So if you remember from the lectures, there are two types of force acting, right? The driving force and the resisting force. So which one will increase when the slope material will get saturated? The answer is driving force. So that is kind of, you can just imagine, right? Like if water is there, then the slope material can flow easily. So what happens when the movement is more? The driving force is more. That is all. So from this, what you have to keep in mind is there are two forces which kind of act on this slope material, which is the driving force and the resisting force. When driving force is greater than the resisting force, that slope material will come down. The component of force of gravity acting tangentially to the surface is known as. So you have a slope like this, just imagine. So gravity is acting like this, right? But it will have, because let's say the material is standing like this. So this G will have two uh, components, one which is perpendicular to it, and the other, like let's say this is GP, which is perpendicular, and then this is GT, which is tangential to it. Yes. So the answer is shear stress, not force. Like we call it as shear stress component. And what is the difference between shear stress and shear strength? Does anyone remember? In this particular context, you can think. Okay, so shear stress is basically that external uh, force which is acting on the surface, and shear strength is something which is related to the property of that material, like the particles of that material, how well they are attached and detached, that kind of thing. The reason behind tilting of the leaning tower of Pisa is, okay, sorry, I gave the answer. Okay, so the answer is accelerated water withdrawal. So the leaning tower of Pisa was initially constructed upright, but then what happened is when the surrounding areas, they there was an increase in the water withdrawal, then that kind of affected the ground, and then the tower of Pisa started leaning. So that's the reason. So I thought I had given options, that's why I clicked it. So yeah, here's the answer. In a rotational slide, the sediments slip on the dash plane. So for this, you have to understand what a rotational slide is and in what plane the sediments will slip. So rotational slide is a movement kind of like this. So from this, can you guess like what is the plane? Okay, that's a good guess, but the answer is curvilinear. Okay, so the answer is curvilinear plane. So rotational, like translational slide is what? If the material just slides and comes down. Rotational slide is when it kind of creates a scooping kind of structure, and then it brings down the material. So that brings us to the end of this. Uh, so if you have any question from today's session or from before, you can ask me. We still have 8 more minutes. So, yeah. Or like if it exceeds, also, I'm fine with that. If you have any questions, you can ask me. I'll be uploading these slides and also the video link. I think they have also shared it with you, right? So you can go through that. And if you have any questions, you can put it in the forum. Any questions regarding tsunami or previous topics? Okay, so Rapunjay, like I am not very familiar with this. Like we have, like I've not been informed the pattern, but I'm assuming that since it's an online exam, you might be having the MCQ type and maybe possibly short answer type questions. But yeah, if I get to know, I'll definitely share it with you people. I don't know as of now, but yeah, I'll maybe put it in the forum. Okay, so if there are no further questions, then shall I stop sharing? Okay, so I think they have provided you a link in your NPTEL platform. I'll just check it. I'll just tell you. I think in that list of courses is there, right? Like week one, week two. So on bottom of that, I think they have given you that link, problem solving thing. You can just check it. It'll be there. Both this video which I have recorded, that will be there, and also the PPT will be there with the questions and all the slides. If you don't have any further questions, then shall I conclude the session? Okay. Thank you so much. It's been wonderful, like interacting with you guys. So I hope I've been able to help you with the subject. And if you have any queries, please feel free to ask. And I wish you all the best for your examination. If you have questions, you can ask me. If not, I'll conclude the session. Like you can leave the meeting. Thank you, Rohini.